Okay, this is section 6.2, and we're going to cover inverse functions and relations. So first we have to recall what a function is and what a relationship is. But let's go and determine our objectives of this section. We're going to find the inverse of a relation and a function and determine whether two functions or relations are inverses of each other. Say our vocabulary is inverse relation and inverse function. So inverse relation is a set of ordered pairs obtained by exchanging the coordinates of each ordered pair. And inverse functions, as with inverse relation, inverse functions are also related. So remember, to be a relation, they have to have an ordered pair, basically. Everybody has to have a partner. To be a function, it has to pass the vertical line test. So we take the graph, you can't have the same input with a different output. So that's basically it for understanding what a function and relationship is. But now we're going to talk about inverse relationships. And when we're talking about that, we're saying if you look at the key concept box, it's on page 393, but it's also on our video notes. Inverse relationships are two relations are inverse relations if and only if, whenever one relation contains elements A, B, the other contains the elements B, A. So basically we're flipping the X and Y coordinates. So for the example here, A and B are inverse relationships. Look at A, the coordinates are 1, 5, 2, 6, 3, 7. And B's are just the opposite, 5, 1, 6, 2, 7, 3. Let's look at example 1 on page 393. It says the vertices of triangle ABC can be represented by this relationship 1, negative 2, 2, 5, 4, negative 1. They want us to find the inverse of this relationship and describe the graph of the inverse. So first we graph triangle ABC, and you see it's right here in blue. It's just coordinates. Then we take these coordinates and we reverse the order. So 1, negative 2 becomes negative 2, 1. 2, 5 becomes 5, 2. 4, negative 1 becomes negative 1, 4. Now we plot those, and that's the green triangle. And if you notice, it's hard to tell. It doesn't look like it because it's sideways. But if you took this line, this oblique linear line, y equals x, which goes to the origin, which is in red, and you would to fold this graph in half, triangle ABC becomes triangle A prime, B prime, C prime. And it reflects over the line y equals x. So, as with relations, the ordered pair of inverse functions are also related. So, how do we write them? So, the function is f of x, and to write its inverse, we write f to the negative 1 of x. This says it's an inverse. Okay, so when you write it, you're simply switching, and you go f of x is the function, and f of negative of x is the inverse. So this is the function. This is how you would write the function. And this is how we would write the inverse of the function. Okay? All right, so now, there's another property of inverses. It says if f, which is a function, and f to the negative 1 are inverses, then f of a equals b if and only if in the inverse of b equals a. So let's look at the example. What are they really saying? So what they're saying is let f of x equal x minus 4 and its inverse be x plus 4. So let's start with f of x. Let's do f of 6. We put 6 into f of x and we get 2. X plus 4 is its inverse if we do f of 2 and it equals 6. So we put 2 into the inverse and we get 6. So because f of x and f inverse of x are inverses, then f of 6 equals 2, and then the f of 2 of the inverse is equal to 6. So basically what we're saying is we're swapping the domain and the range. The domain of the function now becomes the range of the inverse. the range of the function now becomes the domain of the inverse. Okay, so we have a vertical line test to determine if a relation is a function. When we do the vertical line test, it means it can only pass one time. Well, when the inverse of a function is a function, the original function is a one-to-one. We learned that way back when. So recall that the vertical line test can be used to determine whether this is a relation is a function. Similarly, the horizontal line test can be used to determine whether the inverse of a function is also a function. So we have two different functions here. So we do the vertical line test. Yes, it's a function. Is its inverse a function? Well, we do the horizontal line test, and yes, because it only passes once, so it is a one-to-one, which means its inverse is a function. Now let's look at this function here. So it's a function, it passes vertical line test, but it fails a horizontal line test, which determines that its inverse is not a function. So the inverse of a function can only be found by exchanging the domain and the range. And just because it's an inverse does not mean that the inverse is also a function. You could find it, graph it, and run the vertical line test, or simply run the horizontal line test on the function. So let's look at example 2. It says find the inverse of each function, then graph the function and its inverse. So we have f of x equals 2x minus 5. So another way of writing this is to say y equals 2x minus 5. In order to find the inverse, we're simply going to swap the y and the x. So we're going to say x equal 2y minus 5. Now we just do algebra and we solve for y. So we get x plus 5 equals 2y, and I'm going to use a property and exchange these. Divide by 2, divide by 2. So y equals x plus 5 over 2, or I can say f of negative x equals x plus 5 over 2. Okay, so that is our inverse. So we just replace it. All right, and we solved it. So if we graph them both, you see them right here on this graph, you'll notice that they reflect over the line y equals x. Okay, and are they both functions? Yes, they are. They're both linear equations. So now let's look at b, x squared plus 1. So this one's a little different. So we have y equals x squared plus 1. Let me make sure I have it correct. I do. So we're going to exchange x and y. So this becomes x equals y squared plus, we exchange them exactly the way they are, including exponents. So now I'm going to rewrite this because I like my y on the left side. I'm solving for y. So I have y squared equals x minus 1. But I need to solve for y, so I have to take the square root. Remember, when you're solving the equation and you take the square root, you get two values, plus or minus the square root of x minus 1. So how do you, remember this is a square root function. It moves to the right 1 unit, and it does this, the positive. But when it's negative, it's a reflection, and it's going to do this. So if we were to graph, we have two different functions there. So we have to graph both of them, okay? And you see it reflects over the line equals y equals x, but do you notice that here, right here, the sideways u is the plus or minus the square root of x minus 1. It is not a function because it fails a vertical line test, but we could take the original function. So this is the inverse, and the original function is right here. It passes a vertical line test, but it fails the horizontal line test. So without even finding it, or graphing it, we would know right off the bat that it is not an inverse function. Okay? How can we verify inverses? Well, you can determine if two functions are inverses by finding their compositions. If both compositions equal the identity function x, then the functions are inverse of each other. So what we're saying is two functions, f of x and g of x are inverses of each other if and only if both of their compositions, means fog and goff, equal x. Not negative x, not x plus 1, not 1 over x, not x squared, just x, and they both have. So let's look at example 3. Determine whether each pair of functions are inverses. Okay, they don't show that they're inverses by doing g to the negative 1 or f to the negative 1. They want us to determine them. So we're going to do fog, the composition. So we start with fog. So we first start with g of x, which is 1/3 x minus 3. Now we're going to do f of 1/3 x minus 3. We're going to put this into the f function. So 3 times 1/3 x minus 3 plus 9. We have to distribute and use algebra. And then we get x minus 9 plus 9. That cancels to 0, so we get x. So far, we're good. But now we have to do goff. Remember, order matters. So f of x is 3x plus 9. We put that into g of x right here, 1/3 times 3x plus 9 minus 3. We distribute, and we get x plus 3 minus 3, or excuse me, x. And because they're both equal x, we can say that the functions are inverses of each other. We could also take f of x and change f of x to y, switch y and x, and solve for y, and we should get y equals 1/3 x minus 3. That's another way. But we have to know inverses, compositions. So let's look at B, 4x squared and g of x. All right, so we first start with fog. So we start with goff, g of x, which is 2 squared of x. Now we want to find f of 2 squared of x. So we put 2 squared of x into f of x, and we get 4 times 2 squared of x squared. And we simplify, and we get 16x, and we can stop there immediately. We have to check or make sure we didn't make any bad math, but because the fog equals 16x, we can say they are not inverses of each other. They both, fog and goff, have to equal to x, like on example A, in order for them to be inverses of each other. All right, so do your example problems. We'll see you in class.